The race is on to find the fastest available computers to help scientists find answers to questions that could result in vaccines and medications to combat this coronavirus. And while we are still some distance away from fully functioning quantum computers, elements of that technology are already available to deliver badly needed answers. To help us understand what is and what could be, we welcome from downtown Toronto Dr. Shahini Ghosh. She is a professor of physics and computer science at Wilfrid Laurier University, director of the Centre for Women in Science, and president of the Canadian Association of Physicists. And it's great to have you on TVO tonight, Dr. Ghosh. How are you managing through this pandemic?
I'm doing my best, staying at home and, trying to keep my sanity, like all of us.
Those all seem like very wise goals. Let me try this for starters here. IBM apparently has a computer called Summit, and it's supposed to be the fastest supercomputer in the world. It's used by scientists to solve really complex tasks in the fields of energy and artificial intelligence, and right now, most importantly, obviously, health. But I'm told it pales in comparison to what computers one day might be able to do. So why don't we start with this? Imagine that future for us, if you would. What do you see down the road?
Okay, so the first need of the moment for sure right now for the pandemic is to try to find vaccines and treatments. And if you think about it, that's really a question of trying to understand how, chemical reactions and interactions of atoms and electrons, basically molecular physics. And turns out quantum theory is the underlying theory that describes how these kinds of atoms and molecules interact. Now, if you try to model these on supercomputers like IBM's Summit, it's actually very, very challenging because it's really hard to capture every single property of every single electron. So just to give you an idea of why it's hard, try to think about a box of Lego pieces that you're using to try to build let's say, a nice round soccer ball. But all you have are square Lego pieces. So you try to fit them together, and eventually, you can make something that looks kind of round, but it's going to have obviously some errors, and it's going to take a lot of pieces and time and effort. But what if you had a much better Lego box, which had nice rounded pieces? Much better pieces. And with just a few, you could make your nice round sphere. So you've simulated your sphere much more efficiently with your other Lego box. So when we have quantum computers, it's kind of like having this incredibly super duper Lego box that will allow us all the pieces we need to do quantum chemistry. And that's what's going to be a game changer.
This is why we invited you on this program, because you are the queen of metaphors, and you can explain this stuff, which is impossible to understand in terms that we can understand.
Well, I love Lego, actually. So.
Oh, and you're a Lego fan. Good. What other discoveries might be possible once quantum computers do come online?
Yeah, so quantum theory offers, a lot of potential for the future, and especially if you think about public health. As we've all learned through this pandemic, there's much more to this particular situation than just drugs and vaccine development. We have to think about things like, communicating large amounts of data securely. We have to think about transportation, logistics, supply chain questions, testing, sensing. Turns out quantum can actually help with almost all of these areas. One of the things that quantum computing as well as quantum properties allows us is unbreakable encryption, for example. And as we know, information is everything. And we're talking about big data and, for example, private healthcare records all the time. So being able to develop quantum networks, perhaps a future quantum internet that has security built in at a level that is unprecedented, would be really, really useful. So that's one example. Sensing, testing, being able to do high precision measurements is another potential application. And when we talk about big data, one of the things we need to do is to be able to sort through the data, find optimal solutions. So optimization and search turns out to be applications of quantum that also could be hugely powerful. So there's so many different potential applications.
Now, I watched your TED Talk last night in preparation for this, which I don't know if you've looked lately, but you've only got 4 million hits on that TED Talk. Apparently, a lot of people are interested in what you have to say about quantum mechanics and quantum physics, and I'm not surprised why. But one of the things you talked about was the teleportation of information. And boy, I got to know what that means. What is teleportation of information?
It sounds like science fiction, I know, but it's actually possible and doable these days in the lab as a sort of like a proof of principle experiment. What it really means is we're not talking Star Trek level teleportation. So it's not instant and it's not like we can, suddenly disappear from Toronto and reappear in Australia or
It's
anything
not
like
beam
that.
me
Although
up,
that would be
Scotty, is what you mean.
Yes, we can't do that as yet. But what we can do is use this underlying very cool quantum property called entanglement, which connects quantum particles like electrons or photons across, large distances in such a way that they sort of remain connected and provide a communication channel, even though they are at different locations. So using this kind of an entangled channel, we can actually transmit quantum information, basically zeros and ones, if you like, from one location to another using the quantum channel. And that turns out to be useful because, going back to my Lego analogy, it's like having this extra super powerful Lego piece. In fact, it's like having connected Lego pieces, so boxes of, Lego sets across the universe, perhaps, or let's say on Earth, in this quantum internet of connected Lego pieces, which allows us to do new kinds of communication. Collectively, we can do things that we cannot do before. So security, authentication, things like perhaps collective decision making. These are the kinds of applications that entanglement and applications such as teleportation can allow us, as well as part of quantum computers will involve this kind of a transmission of information that's much more efficient in some cases, and that's what teleportation is also useful for.
Well, again, if I can steal one of your wonderful metaphors, the kinds of computers that we're aware of compared to quantum computers is, I think you've said, like candles versus light bulbs. It is that kind of difference. But what is it about quantum physics that makes all of these potential applications that you've just described possible?
So yes, I like to use the candle and light bulb analogy because if you think about it, both of those kinds of, if you like, technologies have the same purpose. They're producing light, but there's no way that you can make a light bulb just by using or trying to improve your technology for building candles. It's just completely different principles of operation that make a light bulb work compared to a candle. And that's also the case if you think about quantum computers compared to our current computers. So quantum computers would work on the principles of quantum physics, and turns out the laws that govern quantum properties are very, very different from what we call classical physics, which is basically everything else that's not quantum. And the reason that we get this big difference, just like a candle and a light bulb, is because those rules can be really, really weird. So for example, I think a lot of people have heard about this law of quantum uncertainty, which tells us that we can't actually know precisely everything about a quantum particle. So if you know precisely the location of a particle, you won't know anything about its velocity, for example, how fast it's going or where it's going. And if you know how fast and where it's going, you don't know its precise location, which is not like any GPS that we know of in our everyday world. And yet that is the quantum GPS. And that seems really weird to us because it's not our everyday experience, but weirdness turns out to be very powerful when you talk about computing. So that's why we now have this entirely new engine that we can use to drive faster for certain applications.
What would be the biggest barriers to building a real quantum computer nowadays?
So actually, there's lots of barriers. I think that we are now at a point in the development of this technology that would be similar to, back when our regular computers were being built, and back in the day, the first computers were, the size of a room. If you think about ENIAC back in the 60s and 70s, you really couldn't do much with them. And in fact, today's smartphones have more computing power than, the computers that took us to the moon. So I think we are in those early days of quantum computers, where in fact the current prototype computers that companies like IBM and Google have, they actually are the size of a room. And the reason they're the size of a room is because quantum computers turn out to be very fragile. The actual chip is tiny, but you need the entire room to build a cooling system to make sure that there's no noise affecting this chip. So any form of heating for current technologies that are being used in quantum computing is really, really a big, huge problem. So we're talking really, really cold, colder than outer space. So that is a huge challenge. And the biggest barrier to being able to scale up these computers is to be able to control these errors that are caused by things like heating and noise. But it's really an engineering problem. I think the theoretical physics is clear. We know that there's all this potential power. It's about now being creative and innovative and solving these real world challenges of heating and scaling up. But we've done it before. Look where we are with our current computers. So, I'm hopeful.
You're hopeful, but having said that, that does sound like quite an insurmountable problem to solve. I mean, I can't even get my head around how you'd achieve that. Can you figure that out?
Well, actually, our current computers also are not perfect. Every time, the computer crashes, that's a very good indicator that we have errors happening in our computers all the time. And the reason they don't crash all the time is actually there's background error correction happening. So for every email you're sending that is not total garbage, it's because it's being checked all the time by your computer to make sure there aren't any errors. Turns out we have similar principles we can apply to quantum computers to do quantum error correction. Yes, it's a little bit more challenging, but again, we have an entire mathematical framework to make it happen. And we know that it works. It's again a matter of being able to build in the resources and design the system in such a way that you can scale it up, not just based on physics constraints, but of course there are constraints of resources, energy use, cost, and so on. Because it wouldn't help if we can't scale it up in a way that is, both energy efficient as well as cost efficient. And those are, I guess, problems that luckily as a physicist, I don't have to address, but eventually they will have to be addressed.
Well, I will ask you to weigh in on this, though, and that is give our viewers and listeners some sense about whether we are, I mean, are we 5 years away from a breakthrough, 10 years, 25 years, 50 years? What's the ballpark we're talking here?
So it's always dangerous to predict the future of technology, and we always get it wrong. So given that, I can sort of give you an idea of where we stand now. So currently, as I said, there are some prototype computers built by companies like IBM, Google. In Canada, we have D-Wave. And they are at the point where they've proved that these are useful for certain tasks, but they're just on the edge of being able to do something that current computers can't do. So currently, those computers can prove that we can do quantum, but they're not quite able to do tasks that no other computer can do on Earth. But that's a matter of scaling. So we have these small computers. In the near term, we will be able to perhaps dream up some problems, perhaps in, for example, quantum chemistry, materials design, types of smaller problems where we try to analyze small molecules. And those could be done maybe in the next few years. Another type of technology which I think is more advanced is not just quantum computing, but quantum communication. So this question of encryption that I was talking about, being able to create a quantum secure internet is something that's been being developed around the world, and some places already have quantum encryption networks set up. And this technology is more advanced. So I would say that this is what would be developed and potentially commercially viable, and also in the nearer term. The longer term dream, of course, is to have that large scale, super powerful quantum computer that can solve problems blindingly fast that nothing that we have currently can touch. And that's, of course, going to be a much longer term effort over decades, but something we have to start now.
Okay, here's the controversial question. Is it going to come from America, from China, from somewhere else? What do you think?
That is controversial, and you're just going to get me into trouble for this, but
that's my job, man. That's what I do.
You're doing it well. I'm hoping actually that we don't go that route, because the way I see it, if you think about the biggest physics experiments and successes we've had, for example, the Large Hadron Collider, which discovered so many fundamental particles, including, the Higgs boson recently. That's an international collaborative effort. The International Space Station is an international collaborative effort. LIGO, which discovered gravitational waves, is an international collaborative effort. The image of the black hole from last year, which was just mind-blowing, that happened because the whole world worked together. So the same thing, by the way, is also happening in quantum computing. I collaborate with international researchers from around the world whenever I can, and so does the community. So on the ground, there's a lot of that kind of scientific collaboration happening. At the level of, governments and policy making, that is, of course, outside of the hands of scientists. But I think we make much better progress to address global challenges such as pandemics and climate change when we do work internationally collaboratively, because it's not just our part of the world that's going to face the challenge. So my real hope is that we're going to be more collaborative, but of course that will depend on how different countries and governments make policy.
I should stop there, but I can't resist asking the follow-up on this. We don't live in times which feel like international collaboration on big stuff is at its best, if I can put it that way. I wonder if that makes you more pessimistic about the possibility of working collaboratively with colleagues all over the world on this.
So I do want to point out, though, that, as a scientist, actually, I don't see that as a problem. I've never felt that I can't, for example, go to China and, participate in a conference and talk about my work. In fact, I have done that. And people do that all the time. Of course, not right now. I can't actually go there, but we still have international conferences and we still do exchange ideas. I think that different countries have certainly invested in different ways in technologies like quantum computing. So China, for example, is far ahead in things like quantum communication. They've launched a quantum satellite that I assume is going to be the basis for building a larger quantum internet. The US has been, focusing on quantum computing. As I said, Google, IBM, they have been developing actual quantum computers. Canada has been contributing right from the start. In fact, the whole field started thanks to some original work that focused on this idea of quantum encryption, and one of the original players in that work was from Canada, Gilles Brassard. So Canada also has been a huge contributor in the field. So I think there's different efforts happening in different parts of the world. Politically, are things going well? Sadly, no. I agree with you that there is certainly reason to be pessimistic. But I'm actually, as you perhaps can tell, an optimist at heart. And I think we can aspire to be better. And we are not going to be solving our global challenges without collaborating. We have the evidence to prove that. So hopefully we will come to our senses.
Amen. Words to live by. Can you take us back just in our remaining moments here? When was the idea or the notion of quantum computing, when was it discovered in the first place?
Well, quantum physics itself is actually something that's been around for over a century. So the first steps towards building the theory started back in the late 1800s, early 1900s. And it's kind of interesting because, of course, the theory itself was so weird that many of the most powerful parts of it were I guess, ignored, I would say, until maybe the 80s. And then the 80s is when computer scientists, together with physicists, realized that things like quantum uncertainty, which seems like something that is not a useful thing, is actually very powerful and can be harnessed. And so I would say that what we would call quantum 2.0, which is using quantum, which already existed, quantum 1.0 existed since the late 1800s. Quantum 2.0, which is really what I would say was the beginning of this idea of using quantum for computing and communication, that started, I'd say, mid-80s.
And in our last 30 seconds here, I know this is a question you could give an hour-long answer to, but I got 30 seconds. How'd you get into this in the first place?
That's a good question. I think it was back in my undergrad days. I was lucky enough to do a summer undergraduate research project. So I highly recommend to all students to try and take on some kind of a research summer project. And it involved quantum physics. And before that, actually, I'd taken a course and it made no sense to me, and I almost failed the course. But then I did this research project, and I had a great advisor, and I just was hooked from then. And it was also strange, and it seemed like the ultimate mystery of the universe. And it blew my mind that all of these weird properties that we don't experience, we can still just use our imagination and our intellect to still try to solve those mysteries and be able to describe this using the language of mathematics. To me, that was eye-opening, and I can't imagine doing anything else now.
I thought the ultimate mystery of the universe was why it's been 53 years since the Leafs last won a Stanley Cup. But no, maybe you're right. Yours is maybe a little bit more impressive.
Well, maybe quantum computers will help us solve that mystery. What do you think?
From your lips to God's ears. Let's see. Shohini
Excellent.
Ghosh, it's awfully good of you to spend so much time with us here on TVO tonight. We thank you so much, and this has been absolutely fascinating. Be well, okay?
Thank you. Thank you for having me. You too.
The Agenda with Steve Paikin is brought to you by the Chartered Professional Accountants of Ontario. CPA Ontario is a regulator, an educator, a thought leader, and an advocate. We protect the public. We advance our profession. We guide our CPAs. We are CPA Ontario. And by viewers like you. Thank you.